So, today we're going to talk about this incredibly powerful strategy that honestly isn't just for computer scientists. It's a mental model, a way of looking at challenges that seem absolutely impossible and breaking them down into pieces you can actually solve. It's called divide and conquer. And I think by the end of this, you'll see how it can totally change the way you approach problems.
Okay, to get our heads around this whole idea, let's start with a classic riddle. How do you eat an elephant? I mean, think about it. It just seems overwhelming, right? Way too big to even know where to begin. And of course, the answer is one bite at a time. Now, this sounds super simple, I know, but this exact idea is the foundation of some of the most elegant and efficient algorithms ever created. The real trick is just figuring out where to take that first bite. To really see this in action, let's swap out the elephant for something a little more grounded. Let's imagine you're a farmer and you've got this plot of land with a pretty tricky puzzle to solve. All right, here's the puzzle for you. You've got this big rectangular plot of land. It's 1,680 meters by 640 meters. Your job is to divide the entire thing into identical square plots, but, and this is the key, you want those squares to be as large as they can possibly be. So, where do you even start? Now, instead of just staring at this giant rectangle and getting overwhelmed, let's take that first bite out of the problem. This is where we get to the brilliant aha moment. Okay, first things first. The easiest thing to do is to mark out the biggest squares we possibly can. Since the shorter side is 640 meters, we know we can fit at least two big 640 by 640 meter squares in there. And just like that, we're not dealing with that massive original plot anymore. We've simplified the problem. All we have left to worry about is this smaller leftover piece, this 640 by 400 meter rectangle. And this is the aha moment. This is the whole secret sauce right here. The biggest square that works for this smaller piece of land is the exact same size as the biggest square that works for the entire farm. We've just reduced the problem to a smaller, identical version of itself. That's the magic of recursion. So what do we do now? We just do the exact same thing again. And again, we take our 640 by 400 plot, carve out a 400 by 400 square, and we're left with an even smaller piece. With every single step, the problem gets smaller and simpler. We're just spiraling closer and closer to the answer. We just keep doing this, shrinking the problem down and down, until we hit a point where it's just dead simple. We end up with a 160 by 80 meter plot. We call this the base case, the simplest possible version of our problem. And here, the answer is totally obvious. The largest square that fits perfectly in that little piece is 80 by 80 meters. And because of that recursive magic we talked about, guess what? That's the answer for the entire original farm. Pretty cool, right? All right, so now that we've seen this thing in action, let's put a proper name to it. What we've just done is a classic example of divide and conquer. At its heart, divide and conquer is all about this idea of recursively breaking a big problem down into smaller, identical subproblems. And you keep doing that until the pieces are so tiny they're a piece of cake to solve directly. So really, this whole strategy just boils down to two simple steps. First, you have to figure out your base case. What's the absolute simplest version of your problem? And second, how do you divide or shrink your problem to get it closer and closer to that base case? Let's look at our farm puzzle again through this lens. The base case, that was the plot where one side was a perfect multiple of the other. Super easy. The recursive case, well, that was any bigger plot, which we knew how to shrink by carving out squares and just focusing on the smaller piece that was left over. Okay, that's awesome for dividing up fields of grass, but how in the world does this help us in the digital world? Let's see how this exact same thinking translates into writing actual code. You might be thinking, okay, that's a cool little brain teaser for a farm, but code? How does this apply to, a list of numbers? Well, it turns out the logic is exactly the same. So let's take a totally different problem. How would you sum up all the numbers in a list, like this one? Sure, you could use a loop, but how would we tackle it with this new divide and conquer mindset? We just ask ourselves the same two questions. First, what's the base case? What's the simplest list you could possibly sum? An empty one. Or maybe one with just a single number, right? The answer is trivial. In the recursive case, we can say that the sum of the whole list is just the first number plus the sum of everything else. We just shrunk the problem again. And believe it or not, This isn't just some weird academic thought experiment. This recursive way of thinking is the absolute bedrock of entire programming styles, like functional programming. Languages like Haskell are built around this idea. They often don't even use traditional loops. Okay, so we've seen this work for a farm, and we've seen it work for a list of numbers. So what's the big deal? Why is this such a powerful concept? Because divide and conquer isn't just one algorithm. It's a mental model. It's a way of looking at huge, scary, complex problems and knowing you have a tool to break them down into something you can actually handle. And this isn't some niche idea. It's the engine behind some of the most famous and important algorithms ever created. You've got quicksort and merge sort, two of the fastest ways to sort a list. You've got binary search, that incredibly fast way to find something. This powerful idea is absolutely everywhere. So this leaves us with just one final thought. Now that you have this powerful way of thinking in your back pocket, think about the challenges you're facing, whether it's in code or just in life. What's the next big, overwhelming, elephant-sized problem that you're going to solve, one bite at a time?